In this video, we will introduce a wideband Fabry-Pérot Resonator antenna with a partially reflective surface composed of equivalent medium metamaterials. Here we show the configuration of the Fabry-Pérot Resonator antenna. The classical Fabry-Pérot Resonator antenna has a waveguide horn embedded inside a cavity between a partially reflective surface and a metallic ground. The partially reflective surface is composed of 4 rotationally symmetric sections with different dielectric constants. Note that the dielectric constant gradually increases from the margin to the center of the surface. A waveguide horn is designed to act as a wideband feeding source of the Fabry-Pérot Resonator antenna. From the simulation results, it can be found that the radiation patterns of the horn are different in E and H planes. Therefore, if a rotationally symmetric PIS is employed in the design of the antenna, the radiation characteristics cannot be well tuned in dual planes simultaneously. To achieve better performance, a non-rotationally symmetric PIS is applied in the antenna design. Since the shape of each section can be optimized according to the radiation pattern of the feeding source, the dielectric constant in each ring of the proposed PIS2 is the same as that of traditional PIS1, ranging from 3.5 to 9.5. However, in PIS2, the 3 inner rings have oval shapes, whereas the outermost ring has a circular shape. To realize different dielectric constants, the metamaterials composed of metallic rings and etching holes are used in the PIS design. From the simulation results, it can be seen that by changing the diameter of the metallic ring and etching hole unit cell, the equivalent permittivity can be effectively tuned to satisfy the design goals. As the thickness of the unit cell and the PIS is 3 mm and 15 mm respectively, the PIS is stacked by 5 layers of unit cells in vertical direction. By comparing the simulated near-field phase distribution of the two antennas, PIS2 exhibits much more uniform phase distribution than PIS1. In the meanwhile, it is clearly observed that the antenna with PIS2 exhibits better performance than PIS1, especially in the radiation gain and bandwidth. The waveguide feeding horn and PIS2 are fabricated respectively. The simulated and measured radiation patterns of the proposed Fabry-Pérot Resonator antenna are in good agreement from 6 GHz to 11 GHz, which validates our theoretical predictions. For more details, please refer to our published paper. Thanks for watching this video.
We introduced a new design of a Fabry-Pérot cavity antenna with an outstanding filtering response based on a novel filtering feeding scheme. It shows great potentials in applying to sensing and communications systems.
The typical way to design an FPC antenna presenting a filtering performance is employing the FSS. However, such FPC antennas usually suffer the drawbacks of limited bandwidth and increased fabrication complexity and cost. Here we introduce a new filtering FPC antenna featuring no FSS used. It has the merits of simple configuration, improved bandwidth, and outstanding filtering response. To validate the concept, we first propose a new SIW-Fed filtering antenna element. It is developed using 2 substrates and 1 piece of bonding film in between. The radiating structure is designed in substrate 1, while substrate 2 is for building the feeding structure. In particular, the slotted patches, user hairpin lines, and a stepped impedance SIW feeding structure are introduced to produce a good filtering response for the antenna. Based on the proposed design concept, the proposed filtering antenna element is then used to serve as the feeding source of the FPC antenna. This figure shows the exploded diagram of the proposed filtering FPC antenna with a waveguide to SIW transition for measurement. Over here are the fabricated prototypes. The measured impedance bandwidth is 15.7% from 56.4 to 66 GHz. The proposed antenna achieves a maximum gain of 16.4 and 15.8 dBi for simulation and measurement. His measured suppression levels are greater than 24 and 27 dB in the lower and upper stop bands. The antenna has a good front-to-back ratio and a cross-polarization level. A comparison between the proposed and the reported filtering FPC antennas is given in this table. Overall, the proposed filtering FPC antenna features the merits of outstanding filtering response and improved bandwidth, in addition to simple configuration. This work was conducted at the Stakey Laboratory of Terahertz and Millimeter Waves, City University of Hong Kong. For more details, please refer to our paper. Thank you for watching.
We are happy to share our recent research entitled A High-Gain and Wideband Filtering Millimeter Wave Fabry-Pérot Cavity Antenna Enabled by High-Pass Source and Low-Pass Surface. I am presenter Cheng from Shenzhen University. My presentation will be divided into 6 parts. First, I will introduce the motivation of the research. Filtering antenna are expected to be implemented in modern wireless communication systems. They demonstrate the feasibility of developing antenna filters into one component. Advantages of the filtering antennas include small size, low insertion loss, and saving the cost of the systems. On the other hand, due to the advantages of high gain, low profile, simple structure, and cost effectiveness when compared with bulky horns or cooperative feed arrays, Fabry-Pérot cavity antennas have received numerous attention over the past years. Hence, focusing on integrating the advantage of filtering antennas and high FPC for millimeter wave application, we propose a high gain and wideband filtering millimeter wave Fabry-Pérot cavity antenna. The design scheme of the antenna is plotted in this page. The FSS provides low pass characteristics for this high-gain antenna. The FPC with curved floor provides a broadband high-gain effect. It is a good candidate for filtering antenna design in the millimeter wave band. The magnetic electric dipole as a feed provides a high-gain, high-pass characteristic with a tunable gain now. As shown here in this page, the gain now can be tuned. This page shows layer-by-layer structure demonstration of the proposed filtering FPC antenna and a vertical plane E-field distribution at frequency range with or without the passband. As can be seen, the top surface of the antenna is FSS. The middle part is a broadband FPC composed of dielectric slab and reflection ground, and the bottom source is a high-pass magnetic electric dipole based on SIW transition. For the filtering response, as obtained in E-field distribution figure, at the stop band, the outcome wave is weak, which means filtering response is achieved. This page illustrates the measurement setup for the proposed antenna and its measurement results. As observed, the center operating frequency of this antenna is around 26.5 GHz. The measured impedance matching bandwidth is 32% from 22 to 30.5 GHz for reflection coefficient lower than -10 dB. The maximum measured realized gain of the antenna achieves 19.5 dBi. The maximum of gain variation in passband is less than 3 dB. The measurement out of band suppression level is 14 dB. The simulated and measured radiation pattern of the antenna are shown in this page. The antenna has a broadside radiation direction. The measured side lobe level of the antenna is -10 dB across bandwidth, which is acceptable for FPC type antenna. The measured cross polarization is around -22 dB. The overall efficiency is 60%. This page shows the conclusion and summary of the design. A new structure of filtering FPC antenna with high-pass source and low-pass FSS for millimeter wave application was presented. It yields wideband and high-gain performances by the proposed FPC. The design principle of each component of the filtering FPC antenna were investigated in detail. The design allows independently control of the radiation noise generated by the feeding source and FSS. That's all. Thank you for your attention.